Okay, let's dive right into this. Your A-level exams are practically right around the corner, so we're going to cut straight through the noise. In this explainer, we are going to master these core database concepts step by step. Look, I know reviewing for exams can feel totally overwhelming, but today, we're going to organize your brain just like a perfectly structured database.
Here is our syllabus roadmap for the explainer. We'll be looking at data versus information, database models, ER diagrams, relational model keys, and finally wrapping up with data normalization. Let's get started.
Section 1. Data versus information. We're starting at the absolute foundation of IT here, understanding the critical difference between raw chaos and meaningful order.
You absolutely need to nail this distinction for your exam. Data is just the raw, unprocessed numbers or facts. By itself, it has zero context. Think of a random list of numbers like 23, 45, and 12. Information is that exact same data, but processed, analyzed, and given actual meaning. If I tell you those numbers are the ages of students in a class, suddenly you have context, right? Interestingly, whether something is data or information really depends on your perspective and whether you've actually derived insights from it to make a decision.
So structured data is the neat tabular stuff, your standard databases and spreadsheets. It's incredibly easy to query. Compare that to the absolute chaos of unstructured data. We're talking social media posts, videos, free-form emails. Unstructured data is super flexible, sure, but it is incredibly complex to explore. Transforming that chaotic unstructured data into structured information, that's the secret sauce that allows organizations to drastically improve their decision-making.
Moving right along to Section 2, Database Models Explained. Now that we understand what data actually is, let's look at the frameworks we use to store it efficiently.
Picture a strict tree-like format. That's the hierarchical model. Notice how every single record has just one parent node, which branches out into multiple child nodes. It organizes things very cleanly, kind of like a rigid company org chart, but it has a major flaw. You can't easily represent complex relationships where a child might need to belong to more than one parent.
To fix that rigidity, we get the network model. It completely solves that problem by allowing many-to-many relationships in a graph-like structure. Records can interconnect dynamically. But, and here is the key trade-off to remember for your tests, while it's way more flexible, it makes navigating and designing the data so much more complicated because it relies on these deep, complex pointers.
Now, a really crucial concept is comparing traditional relational tables to the object-oriented approach. In a purely relational setup, it's just rows and columns. But the object relational database model, it's a hybrid. It uses blueprints called classes. Think of a class like a recipe for a car, to create interactive objects, like a specific red Audi. This setup lets the database store not just raw values, but actual behaviors or methods, merging standard table storage with advanced programming logic. It's really cool.
All right, Section 3, Mastering ER Diagrams. Let's shift gears and look at the actual blueprints of database design because you are definitely going to have to draw and interpret these in your exam.
First up, entities. An entity is literally just a distinct thing in the real world that we want to store data about. A person, a place, or even an abstract concept like a course enrollment. Now listen closely because here is a massive pro tip for your exam revision. When you're reading a system description and a prompt, underline the nouns. Seriously, those nouns are almost always your entities.
Once you've spotted your entities, you need to describe them. You do that using attributes. If your entity is a student, your attributes are things like the student's name, their age, their ID number. Keep in mind that when this blueprint finally becomes a real database, these attributes turn into your columns. Also remember that the specific set of valid values an attribute is allowed to hold is called its domain.
So how do these entities interact? Relationships. And just like you hunted for nouns to find your entities, now you're hunting for verbs. For example, a student learns a subject. That action, learns, is represented by a diamond shape in your ER diagram, and it completely dictates how those entities talk to each other.
Then we have cardinality, which is really just the numbers game. It defines the quantitative relationship between entities. Think of a one-to-one scenario, like one man marrying one woman. Contrast that with a one-to-many scenario, like one man owning multiple vehicles. Getting your cardinality right is absolutely essential. If you mess this up, your tables won't link together correctly later on.
Section 4, Relational Model Keys. Okay, let's dive into the actual mechanics of the relational model, where we turn those theoretical diagrams into functioning, real-world tables. If you remember literally one thing from this entire explainer, make it this golden rule. Without a unique primary key,
Your relational table is fundamentally broken, period. A database just cannot function if it can't definitively tell one row apart from another. These are the specific keys that lock your whole model together. The primary key, that's your main, unique identifier. The foreign key is what you drop into a totally different table to establish a relationship. What if one single column isn't enough to be unique? You use a composite key, combining two things, like student ID and course ID. Then there's the super key, which is a broad set of columns that guarantees uniqueness even if it has some extra unnecessary fluff. And finally, a unique key is basically a primary key, but it actually allows for a missing or null value. Knowing how these play together is exactly how you block duplicate records. And finally, Section 5, Data Normalization. We've reached the polish. This is the ultimate process of organizing our tables to achieve absolute efficiency. You might be sitting there thinking, especially if you're used to Excel, why can't we just throw all our data into one massive flat table? Well, the answer is to prevent absolute catastrophic chaos when you try to update records. A massive, unnormalized database becomes bloated, painfully slow, and a total nightmare to manage.
Normalization systematically chops that related data up into distinct tables to minimize redundancy. This protects us from those dreaded anomalies. For example, an update anomaly happens if a student changes their address, and you have to update it in 50 different rows instead of just one. Miss a row? Your data is instantly inconsistent. Or imagine a delete anomaly, deleting a student's enrollment record and accidentally deleting the entire existence of the course from your system. That's a total disaster. Normalization solves all of this. These are the exact types of inefficiencies we are trying to absolutely destroy here. Storing the exact same employee record multiple times in different rows, or repeating the exact same department names and IDs across different student records and columns? No way. Normalization ensures every single piece of data is stored in exactly one place.
As you hit the books tonight, I want you to challenge yourself. Pull up a raw, messy table from one of your past papers. Can you spot the functional dependencies, where one attribute dictates another? Can you actually apply these rules and bring order to that chaos? Mastering that process is the true secret to acing your database design questions. So, the next time you look at a chaotic, bloated spreadsheet, ask yourself, what hidden anomalies are just waiting to break this entire system? Keep that in mind, and good luck with your revision.